Hello, welcome back. And now, before going on with Proposition 4 in Book 1, which happens to be the first theorem in this book, and therefore the first theorem in the elements collection, I want to just note here this bit at the beginning. Because it appears to me as though some pieces are missing. According with this sentence, I think, if I'm reading it correctly, the foregoing, that's what's going to happen next, has been selected, okay, out of the regular course. So I'm not sure why that would be the case, but it seems as though there is a regular course and there's what is presented here, and the two are not the same. So that might explain why in the following, I made a bunch of notes now. I figured out how to make notes. I don't know, I can edit this. Here's the definition of produced that I couldn't find earlier. And definition of solution. This is where the straight edge compass is indicated. And I haven't actually gone through to locate these corrections, but anyway. Proposition 4 is described as a theorem, and in it, there's a part here which I think probably would have required at least a demonstration or another theorem prior to this one in order to make the statement. And the statement you'll see in a minute. So I'm just going to jump right to it, and I've copied this text into my thing. Not here, but the previous. Okay, now sorry about the jaggedness of these figures. I have this circle thing, but it only does full circles. I need to make a thing that does, what do you call them? A chord, like a partial, a piece of pie out of a circle. So instead, I just made these figures quickly by drawing lines and hoping it would come out okay. I think it's understandable anyway. Proposition 4, Theorem 1. Yes, missing space? Yeah. If two triangles have two sides of the first equal to two sides of the second, respectively. No, I reworded that slightly. I should probably reinsert. If two triangles have the two sides of the first equal to two sides of the second, respectively. That's difficult to say. I think even in what I would call regular English, this very simple idea, but what it is meaning to say is that there are two sides in particular of the first, and respectively, that is in the same order, those sides are equal to the corresponding sides in the second triangle. That's very long-winded, and I don't know a short way to say it. Essentially, what they're saying is is written in a much clearer, much clearer form this way. That is, red equals red and blue equals blue. Red, blue. That's what they're saying. You see how efficient this mode of communication is? And the angles, yellow and yellow, contained by those equal sides, which is what they are, also equal. Then their bases, or these sides, the whites, are also equal. This is the conclusion. I should probably put that in a different color, maybe. Also equal. Oh, I copied. This should just have a comma here. And the beginning part of this is a typo, a repeat. And we'll try it in a different color. I'm going to bring these here in line. I could have just put text, I guess. It looks like dashes. That will go there approximately. There we go. I can't actually, unfortunately, I can't select this. The text text is the topmost always. So I can't. Never mind about that message. There we go. Okay. Now, let me just get some of this. Maybe that much. Add that to the end here. And then we take some of this one. This may or may not fit. So I can fit half of it, but I don't want half of them. I don't want half and half. So I don't want to get rid of that. Put it back the way it was. Green. That is this blue angle should fit. There we go. Okay. That is. Let's start from the beginning again. If two triangles have these two sides the same, respectively, in the same relative positions, and the angles that they contain being equal as well, then the conclusion is in green. Then their bases, that is, I usually say that is, reformation of a restating of the same thing. Then their bases, that is, the sides indicated as white, are also equal, and the remaining of their remaining angles opposite to equal sides are respectively equal, that is, these angles are also respectively equal from the two triangles, and the triangles are therefore equal in every respect. Okay, you learned this in high school, and maybe took it as given or obvious. There's nothing obvious about it. It has to be proved from the axioms. So what we have is this and this angle equal. Okay, but it's lengths and angle, right? Whether or not that means this is parallel to this is anyone's guess. All we know, actually, we know that their lengths are equal. However, since the angle here is equal, that means that the way that these lines diverge from this vertex is would be in the same direction if we lined it up properly, because they subtend the same angle. So by definition, the subtending of something by some angle is the inclination of the lines, right? So they will have equal inclination if I line one or the other of these two lines up, and then these red ones and the red line and the blue line will lay flush against each other. Okay, if you were to imagine this in 3 dimensions, and I pull this thing out and I stick it on top of this one. In fact, that's what they do. Say, take this thing and just kind of put one or the other, push it on top of this other one. So take it out of the page and push it in. Now, what I've done is try to draw a picture of that. Now, we know the red and the blues are equal, and so are these angles. And here I'm trying to illustrate the pressing of this one with these aligned together with the other one. Alright? Now the argument says, moving the plane figures together, the above lines will coincide. That means they will be coincident at every point. That is, touching essentially. If I want to demonstrate coincide, here are two lines. Now they coincide. You see what I mean? That's what coincide means. And the assertion here is that they will coincide. In fact, they will, because the inclination is the same, and the length is the same, and everything's the same, so therefore they will coincide when we press these two together. And in fact, the word press, I think, is used. Together. Oops, I want the hand. Then their sides or bases are also equal. Okay, now the argument says, let the two triangles be conceived to be placed that the vertex of one of the equal sides that the vertex of one of the equal sides, angle, this should say, oh, it does say angle, sorry. One of the equal angles, yellow and yellow, right? The vertex here, which we could, if we wanted to, we could give a label, V, the vertex. Okay, we could call this V1, or V2 actually, and maybe V1. So if the vertex, if these vertices are brought together, shall fall upon that of the other, and red to coincide with red. So let us take that as the method being employed. Then will blue coincide with blue if apply, not press, but apply. I think to apply means to move together, right? I'm applying this to this by pressing them together. Consequently, the bases indicated in black, which is white for me, will also coincide. Now here's the part that confused me for a while, but I think I've sorted it out. What's missing? There's either a theorem missing or postulate or something, because this here doesn't follow immediately. There's a step missing. Here it says, or the straight lines will enclose a space, which is impossible, and therefore they do coincide, which would imply that the blues equal to blues and reds equal to reds, and so on. Alright, this is my attempt at trying to pull apart the wording and make explicit what is meant by coincide as well as enclose a space. Now, I believe that what they mean by enclose a space is that if the figures are pressed from the side, as in the diagram, the equal lines, these ones, by the definition of being equal, will lay flush against each other. They will coincide in the same sense that I showed you before. Now, seeing that they coincide and essentially become one, it follows that the endpoints of either of those lines also coincide. If the lines coincide, then everything about them is coincident, including the endpoints. So at the bottom here, at the endpoints, which are also the endpoints of the base, okay, where we have the two baselines for each of these triangles. Those bottom lines, now this is, I don't believe Aristotle had written his organon at this point. In fact, I think Aristotle came later, not much later, but, well, maybe not. In any case, there is an axiom of logic here. This axiom, A or not A, is an axiom presumably cannot be proven. It's taken as intuitive, self-evidently true. A or not A. So if we apply that axiom, then the bottom lines must either be coincident or else not coincident. Okay, there are only two possibilities, true or not. And if we suppose that they are not coincident, and also recall that they have the same end point, okay, so they're coincident at the end points, but not coincident in general, then they are touching at the ends, that is, the ends are coincident, that much we know, but not in contact. Coincident means they're fully flush and in contact at every point. But if they're not coincident, that's our assumption, then they are not in contact somewhere else between here and here, and that's the definition of in two dimensions of enclosing a space, right? Like this. In my fancy handwriting mode. Here's one line, and different color. Here's another line. I'm going to try to make these lines. Okay. Between here and here, these lines are not coincident. Forgetting about this little bit at the end here. From here, where they are coincident, to here, also coincident. The fact of these two lines not being coincident at every point between these 2 points where they are coincident implies that the lines enclose a space. They must somehow be separating somewhere. And there's a theorem that said, one of the axioms, axiom 10, says that two straight lines cannot enclose a space, right? But we've just shown that since they're not coincident, they must enclose a space. That's the meaning of not touching, and that's an absurdity and contradicts axiom 10. So therefore, they must be coincident. Okay. Another way of saying it is, well, duh, but that doesn't count usually in things like logic and math, because we have rules, and the rules should be able to be applied mechanically without appealing to, well, duh, which is human intelligence. Human intelligence, although required to build such systems, is not something that we're allowed to use in order to prove something. The proof should be valid and demonstrable to a non-intelligent object, like a computer, let's say, and so we're not allowed to say, well, duh, essentially. Now that theorem is proved, though. We didn't have to appeal to the well, duh. We used the axiom of prepositional logic, that a thing is either something is true or it's not true, and we assumed that it was not true. We were trying to show that they're coincident. We tried seeing what happens if they're not coincident, we noted that the endpoints are coincident, and that in turn, because of the fact that they are not touching somewhere in between, by assumption, by hypothesis, which in turn implies that they enclose a space, which in turn implies a contradiction to axiom 10, which states that two straight lines may not enclose a space. We get the result that the two triangles are in every respect equal. Now that's proved, not just may be sort of true. It follows by the axioms of logic and geometry, for figures. Don't worry about that box. I think I know how to fix that law. Nothing bad happened, but something, how shall I say, one of the assumptions I'm making failed, and it fails. You notice it didn't fail all the time, and I know why that assumption fails. It's because of a case I'm not taking care of. It's nothing for you to worry about. Okay, so that theorem is proved. I don't think that there's any argument one can make against this proof. I believe it follows exactly the axioms and whatever else we've been given, and we didn't appeal to anything else other than what we've been given in order to prove it. That's our goal. That's our intention. Now, another thing, the next one is also a theorem, proposition 5. See my time. Okay, I'll get to that next time. Proposition 5, I believe, as well, relies on something that has been omitted from this version of the text. Okay, anyway, hope you understood that one. I hope I understand it. I want to make sure that I'm not missing something, and I'm not overlooking something or assuming something that I'm not allowed to assume. That's the essence and the goal of rigorous proof, is to make sure you do everything possible you can to identify what you might be assuming unknowingly. Okay, till then.